Hey everyone, let's dive right into this explainer and discover how a simple grid can literally map our entire physical world. Today, we are unlocking the fascinating chapter of coordinate geometry, unpacking the actual mechanics of how we translate the physical 3D space around us into elegant, manageable numbers.
Let's start with a highly practical puzzle drawn directly from our source material. Picture this. Town B is located exactly 36 kilometers east and 15 kilometers north of Town A. Now, if you were tasked with finding the exact straight-line distance between them, how would you calculate that gap without laying down a giant tape measure across the terrain?
To solve this, we're going to look at just two main mathematical tools today, exploring exactly how they work and why they are so incredibly useful. Our agenda will cover geometry meets algebra, the distance formula, proving shapes with distance, the section formula, and finally, the midpoint special case.
All right, let's kick things off with Section 1, Geometry meets Algebra, Bridging the Gap.
You know, we often think of algebra and geometry as completely different subjects, almost like they live in separate worlds. But treating our physical reality as a measurable grid absolutely bridges that gap. It powers the foundational math behind a huge array of real-world applications, from everyday navigation systems and structural engineering to locating the epicenter of earthquakes and seismology and even generating digital art. It's everywhere.
Which brings us right to Section 2, the distance formula, measuring on a grid.
Notice the inherent magic hidden in these grid lines. The split second you drop perpendicular lines from any 2 points straight down to your x and y axes, you automatically visualize a right-angled triangle. It's like unlocking a mathematical cheat code.
Because of that triangle, we don't need to invent entirely new math to find that diagonal distance. We can just use our old familiar friend, the Pythagoras theorem. Step 1, draw those perpendicular lines. Step 2, measure the horizontal base and the vertical height. And Step 3, simply apply the theorem to find your hypotenuse. Super intuitive, right?
So here's the real kicker. That intimidating-looking distance formula you see in the textbooks, it's literally just a squared plus b squared equals c squared, cleverly disguised to work on a grid. The x-coordinates give you the base, and the y-coordinates give you the height. Applying this to our two towns, that 36 kilometers east and 15 kilometers north simply becomes the base and height of our mathematical triangle.
Let's transition into Section 3, Proving Shapes, Using Distance.
We have a wonderful question here straight from the source material. Imagine three students, Ashima, Bharti, and Kamela. If we just look at the coordinates of these three students sitting at their classroom desks, can we mathematically prove they form a perfectly straight line without ever needing to pull out a ruler?
If we map out the classroom, we find Ashima at 3.1, Bharti at 6.4, and Kamela at 8.6. Now, visually, sure, they seem to form a line. But in mathematics, appearances aren't nearly enough. We need absolute, undeniable proof.
And this is exactly where we put our formula to work. By crunching the numbers with our new tool, we find the exact distance of each segment. The distance from Ashima to Bharti, segment AB, calculates to 3 times the square root of 2. Bharti to Kamela, BC, is 2 root 2. And the total spanning distance from Ashima all the way over to Kamela, AC, is exactly 5 root 2. Look at that! 3 plus 2 equals 5. Because the smaller segments add up perfectly to the total without any deviation, it mathematically proves they are sitting in a perfectly straight line. No ruler required.
Now for Section 4, the section formula, finding exact points.
So, what if you don't actually want the total distance, but instead you desperately need to find a very specific spot? Imagine a telephone company needs to place a relay tower exactly 1/3 of the way between two towns to balance their network signal. If they put it right in the dead center, it's wrong. It has to sit at a precise 1:2 ratio along that path. How on earth do we map that specific coordinate without just guessing?
Enter the section formula. This is a real game changer. It allows us to pinpoint the exact x and y coordinates that slice a distance into whatever ratio we need. By multiplying the coordinates by our desired ratios, which the formula calls m1 and m2, we basically weigh the line to find the exact perfectly balanced position. It is an incredibly powerful spatial planning tool.
Which brings us to our final stop, Section 5, the midpoint, splitting in half.
Just notice how beautifully the math cleans up here. On the left side, we have the full, somewhat heavy section formula, but when the ratio is exactly 1-to-1, meaning perfectly in half, those complex m variables simply vanish. They cancel out entirely. And that leaves us on the right side with a simple, incredibly elegant average of the coordinates. You just add the x's and divide by 2, then add the y's and divide by 2. It's a stunning example of how deep algebraic formulas can suddenly simplify into pure intuitive logic.
Which leaves us with this final thought. The very next time you're navigating a massive open-world video game or watching your rideshare approach as a little moving icon on your phone, ask yourself, which of these elegant formulas is quietly working away behind the screen? How is coordinate geometry mapping your world right now? Thank you so much for exploring this fascinating chapter with me today.